the leading United Nations platform on artificial intelligence. Organized by the International Telecommunication Union, the United Nations Agency for Digital Technologies, in partnership with over 50 UN agencies, and co-convened with Switzerland. The mission of AI for Good is to unlock AI's potential to serve humanity. As a multi-stakeholder platform, AI for Good advances solutions, standards, and skills. In today's AI for Good event, we are counting on you to use the live video wall feature to ask questions and post comments to help create an engaging session. Boost your AI skills and elevate your career with the AI for Good Discovery Badge. Receive verified digital credentials that recognize your engagement in cutting-edge sessions, exploring how AI is being used to tackle global challenges. To see if a session is eligible, look for the blue badge banner on the right side of the video interface that activates at the end of each live session. Share your badge on LinkedIn and across your professional profiles, and check the AI for Good events webpage for upcoming eligible online sessions. Discovery Badge sessions are part of the AI Skills Coalition, Ai2's global initiative to strengthen credible AI learning pathways and expand access to high-quality, trustworthy AI knowledge worldwide. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished facilitators and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
And hello everyone, and welcome to this session on AI for fast and flexible climate modeling today. I'm Lu Tian, and a postdoctoral researcher at Max Planck Institute for Biogeochemistry, and I'm also a member of the ALICE European Library for Learning and Intelligent System unit in Vienna. It's my absolute pleasure to introduce our speaker today, Dr. Oliver Watt-Meyer. Oliver leads the climate modeling team at the Allen Institute for Artificial Intelligence. His work at the forefront of integrating learning with atmospheric science to make the climate model faster, more accessible, and more accurate. Before his current role, Oliver earned his PhD from the University of Toronto in 2016 and served as a Novel Climate and Global Climate Change postdoctoral fellow at the University of Washington. Today, alongside his work at Ai2, Oliver also served as an affiliate associate professor in the Department of Atmospheric and Climate Science at the University of Washington. And he also is an associate editor for the Journal of the Advance in Modeling and Earth Systems. Across all these roles, his driving motivation is to better understand the atmospheric variability from subseasonal to centennial timescale. During the presentation, please free to type your question into the chat of neural network, and we will discuss them together during the QA part at the end. Okay, so please join me in welcoming Dr. Oliver Watt-Meyer. Oliver, over to you.
Thank you so much, Lou, for the kind introduction. Very excited to talk to you all today about AI for fast and flexible climate modeling. So I'll be presenting this work on behalf of the whole Ai2 Climate Modeling team, which is shown here. So we're not a big team, but we have been pushing the state of the art for AI and climate modeling for the last few years. And we also work really closely with a variety of external partners, which I'm showing here in the bottom right. So the M² Lines Group from NYU, the National Labs GFDL from NOAA, and Lawrence Livermore National Lab from DOE, and also NVIDIA. So just a little bit of background, as you might not have heard of my institute, the Allen Institute for AI. So this is a Seattle-based nonprofit funded by the Paul Allen Estate. Our mission is to build breakthrough AI to solve the world's biggest problems. And our climate modeling team sits within an AI for the environment section. And the goal of our team is to use machine learning to make faster, better, and easier to use climate models. And as mentioned before, we have partners that we work with very closely, traditional climate modeling labs who provide us with data sets, and also fellow machine learners who we exchange architectures and ideas with. Before I jump too much into talking about climate modeling, I did want to talk a little bit about another project that's ongoing at the Allen Institute for AI, which may be of interest to some of the listeners. And so that's the OMO Earth project. So this is a new platform that was just released a few months ago. This is a geospatial AI foundation model trained on a variety of satellite remote sensing data sets. And additionally, it includes a platform for users to actually be able to easily fine-tune models on custom data sets and allows wide range of applications that's shown here on the right. So just to show one of these particular examples, some of the focus here is on food security, and so be able to quickly analyze changes in food production, potentially based on flooding. And already these tools are being used by multiple governments, which is really exciting to see. So yeah, feel free to check that out, search for OMO Earth. And coming back to climate modeling specifically, just to start at high level, this might be familiar to a lot of the folks listening, but how do we currently plan for climate change? Well, one of the ways that we start this planning process is by doing a set of coordinated experiments with all the leading climate models around the world. And so this is the so-called CMIP, Coupled Model Intercomparison Project, which is a key ingredient. These simulations are a key ingredient in our confidence and understanding about the human influence on climate. And so this has been great. It's been a real advance in terms of understanding the uncertainty and the what we're more confident about in terms of climate change. And these are a key ingredient that go into the IPCC reports on climate change, which come out every 5 to 10 years. So it's great, but on the other hand, there are some challenges with these simulations. They're very computationally expensive. A lot of the climate modeling centers expend a huge amount of their resources actually just doing the simulations, where really we want them to be mostly focused on improving their models. There's also stubborn uncertainties, which have not really been reduced over subsequent generations. And the core spatial resolution makes it difficult for end users to really take action based on these simulations. Often additional manual downscaling or bias correction steps are required. So our team, again, is applying AI to make these sorts of climate models more accurate, faster, and easier to use, and to make this kind of climate information more actionable. As a bit of background, with physically based weather and climate models, which is still how all of the, I would say, the leading state-of-the-art climate models work today. These are based on the laws of physics. We have modular components for the ocean, the atmosphere, land, sea ice, and we simulate climate basically as the statistics of weather. So we do log simulations where we're actually resolving weather timescale variability, and we can average these to get the relevant statistics of interest for climate. And we can see how those change under changing boundary conditions like CO2 or different aerosols. So this enables seamless prediction. In principle, the same model can be used for anything from weather prediction out to centennial scale climate projections. And so in some ways, that actually is analogous to ML foundation models, where you can have one model which is used for a variety of purposes. And of course, just like in machine learning, in this physically based situation, we typically do adjust certain aspects of the model for particular applications. So tuning parameters for particular context. So how does machine learning or AI come into this? Our group has actually been working on this topic since 2019. So we've tried a wide variety of approaches. And so, really, I would say the goals for what we want machine learning to do is to make these models more accurate, potentially make them faster, and also make them more computationally affordable and easier to use. And so the three, these are not totally exhaustive, I would say the three kind of biggest approaches that have been taken, thinking here mostly about the atmosphere, would be machine learning for some kind of post-processing or bias correction. And so this has actually been done for decades, often using simpler statistical approaches, but now also using more sophisticated deep learning strategies. And then some kind of hybrid approach where the machine learning is either replacing or correcting part of the atmospheric model, but it's working in concert with the rest of the numerical model. So this can be like replacing one of the physical parameterizations in the model or all of the physical parameterizations, or doing some kind of online bias correction as the model's predictions are evolving. So there's been a lot of effort in that direction. That's what our group initially started working on. And then finally, it was kind of the more drastic approach of actually having machine learning basically replace the full model. And so it'd actually be representing the evolution of the atmosphere and could fully replace physics-based global atmospheric model. And so I'm going to just kind of go over a few different of the latest models that have been released by other groups before coming back around and talking about what our group has done in the last few years. So on this hybrid approach that I mentioned, the sort of second out of those three options, I would say that the best example of this so far is the neural GCM model from Google Research. So here they coded a spectral dynamical core in JAX. And the advantage of that is that it allows them to optimize their machine learning, which is representing all of the what we call physics. So basically the things like radiation and clouds and turbulence, things that cannot be explicitly resolved by the dynamical core, which is representing the large scale airflow. So all those things can be optimized, but they can be optimized accounting for their interactions with the dynamics and with that fluid flow. And that was the breakthrough that previous approaches had not been able to do because they were trying to interact with existing dynamical cores, often written in Fortran, that didn't allow this kind of optimization that accounts for these interactions. And so these models were able to have very good weather forecast skill, and as well as at least some of the simulations were able to roll out for 40 years and represent the historical warming over the last 40 years, which was definitely a breakthrough. The DELISIM models is deep learning for Earth system modeling. So this is now more this so-called full model replacement, where basically we have one AI model which is representing all of the variability within the atmosphere. And so this was based on using a UNet with convex blocks and evolved out of a weather forecast system developed at the University of Washington by Dale Duran's group. And they actually did include a simple coupling to an ocean model, which was just basically a sea surface temperature ocean model, but they were able to emulate or actually spontaneously generate ENSO, but the variability was much weaker than what we see in reality. But this was definitely a nice breakthrough in terms of, again, enabling long, stable simulations, at least of the current climate. And now finally, for a kind of a fairly different approach, the so-called climate in a bottle or C-bottle. This was developed by folks at NVIDIA. And here, this is a generative model where we can generate particular samples of atmospheric conditions, conditioned on, in this case, something like the sea surface temperature field. So given a particular sea surface temperature field, what are the conditions? What is a plausible sample of conditions throughout the atmosphere? So this worked quite well in terms of getting the trends within sample, but is, I would say, more challenging for extrapolation for SSTs while outside the training data set. And it also doesn't have, makes it a bit harder to probe different time scales of variability because there isn't an autoregressive element kind of baked into the model. So that leads me to an approach that we've taken here at AI2. So we developed something we call the AI2 Climate Emulator, or ACE. And so again, we seamlessly derive climate as the statistics of weather, just like physics-based general circulation models. That is, we actually simulate weather variability, and then we can compute our relevant statistics that we're interested in based on that. Our group has really focused on climate accuracy. We've thought a lot about generalizability to unseen climates. And also coupling to other Earth system components. So a lot of the AI work has been really focused on weather prediction, and that meant it's really been primarily focused on the atmosphere. We are interested in climate modeling, so that necessitates coupling to ocean and other components. And then finally, to kind of address these foci, one of our strategies has been to actually train on climate model output and not just historical reanalysis and not just the ERA5 data set. And this actually lets us both train on a diverse range of climates, so we can do simulations in a future global warm state, and we can directly learn from those. And actually lets us rigorously test the generalizability to unseen climate scenarios. So if we are just training a model on ERA5 and we do some kind of perturbation to see how it works, in a possible future climate, we don't really know what the right answer is. But on the other hand, if we do this with the output from numerical model, we can generate synthetic data to actually test, in a quantitative sense, how well we do at generalizing in this kind of situation. So it's a very powerful tool. We've kind of done a lot here, so I am going to go through some of these results in more detail. But before that, I just wanted to give sort of a high-level overview of the steps that we've been taking over the last few years. So the first ACE model is now kind of came out about 2.5 years ago. And the breakthrough there was having this long-term stability and very accurate timing climate. And so in that case, we were using this sort of idealized setup where our boundary conditions were just annually repeating climatological sea surface temperatures. So it's a very simple setup. We weren't expecting to get any trends. We were just testing, is the timing climate that's simulated by our model accurate, and can we get very long stable simulations? And we were able to do both those things, which was a nice breakthrough. With our next step, we then were focusing on getting realistic both historical and future climate change. So for the historical period, we could train on ERA5, and we could get those trends of warming over the last 80 years. And then for the future warming, for example, be able to simulate a quadrupled CO2 case, we trained on climate model output as training data to allow that. And then now our kind of two more recent advances. One is what we call Samudra. So this is a coupled atmosphere-ocean model. And so we worked again with these partners, M2 from NYU. So they had developed an ocean emulator, Samudra. We had our atmosphere emulator ACE. And so we coupled these two together, made a few changes, and we were able to emulate actual coupled atmosphere-ocean models, in particular GFDL's CM4 model, in pre-industrial conditions. And again, we were able to spontaneously generate El Niño events, which was pretty cool. And then more recently, thinking towards applications and some of the types of users of these models. A lot of those users might be looking for more local scale information. So all of these previous models I discussed were all still operating at 1 degree or roughly 100 kilometer resolution. So we developed this HERO ACE model, which can downscale the outputs of ACE to 3 kilometer resolution. And this is trained on a global storm resolving simulation. So we can get precipitation at much more local scales. Okay, so this is kind of the broad overview, and I'll talk a bit more detail now about these different advances and how we got here. So in general, the way we train these models, and there are a few different flavors in the different generations, but in general, this is kind of what it looks like. Is we have some set of inputs. Here I'm just showing a subset of those with things like humidity, winds, temperature at different vertical layers. We use 8 different finite volume terrain following vertical layers. And then we predict these same fields and also additional fields 6 hours later. So here I'm showing, again, these humidity, wind, and temperature, but then also a lot of the fields that are necessary for interpreting the energy and moisture budgets in climate models. So things like the precipitation or evaporation, and also the radiative fluxes at the top of the atmosphere at the surface, which we need to close energy budgets. And then the loss function will typically be something like a mean squared error over the 6 hour prediction. And then also in more recent models, we are using stochastic loss functions like CRPS. So all of these models, we're not just trying to get the right mean climate, but we also get realistic weather variability as they proceed. So here I'm just showing the outgoing long wave radiation. This is based on our first generation ACE model. And just for 100 days of the simulation, although this looks similar, as you go forward further in time. But what we can see is that even though there's actually no explicit prognosis of clouds in the ACE model, based on the profiles of temperature and specific humidity, the model is able to infer where clouds are, and we can see that we have less outgoing long wave radiation. For example, in the tropics, where we have deep convection, we have very cold cloud tops. And so this is really nice, and we can see these sort of weather systems evolving in the mid-latitudes. You will notice if you look carefully, there's a bit more smoothing in the ACE prediction. So this was kind of a feature of the deterministic mean squared error loss function we used in our initial models. But we've improved this in the latest models where we use CRPS for training. Our group is really interested in physical consistency. So for climate models, we care a lot about interpreting why there are changes in certain terms. And so to be able to do that kind of interpretability, it's very useful to have budgets which we expect to be closed in the real world to also be closed in these models. So here I'm just going to show one example, which is the change in total water path. So this is just a vertically integrated amount of water in a column. And so on the left, this is showing the tendency, so the change in that quantity over a single 6-hour step. And so this is not something that's actually predicted directly by ACE, but we can diagnose it based on the individual humidities at the different layers in the model. And now ACE does predict these middle columns, the evaporation, the precipitation, and the advective tendency, which is just the airflow moving the water around. If we add up these terms, we expect them to, basically sum to zero. So the right-hand column here should be exactly zero. And in the top right, this is based on the training data. So in the model that we're emulating here, that was exactly true. These terms add up to zero. And you can see that they're actually very close to adding up to zero as well in ACE. And this was actually a model which did not impose any particular constraints. The model learned this balance, which was present in the training data, and was very close to obeying that balance in its predictions as well. Now, in our later models, we did exactly impose this constraint because there are some small imbalances in the global mean, but we were able to do that without really affecting the learning process at all because the model did so well in the first place. Moving on to our kind of second ACE2 model. So again, as I said earlier, this was trained on the ERA5 reanalysis, and our goal was, can we replicate the warming trend over the past period and a lot of other features in ERA5. So this was showing that we are able to do that. And so again, this is a model which is forced by the sea surface temperature. So that's a boundary condition which we provide to the model. We also provide the carbon dioxide concentration. And so as you can see here in black, this is showing the global mean and annual mean 2-meter air temperature. And our ACE2 ERA5 model is able to replicate that warming trend. And it also gets some of the wiggles from year to year, which are due to El Nino basically having warmer, we expect warmer globally average temperatures during El Nino years. Training on ERA5 obviously has the big perk that ERA5 reanalysis represents a lot of variability, which is difficult for a lot of coarse resolution climate models to capture. So some examples of that would be, tropical precipitation variability, like the Madden-Julian oscillation, or other convectively coupled equatorial waves. And so you can see that on the left here, that the model does quite a good job of representing a similar kind of variability as what we see in ERA5. And then also for tropical cyclones, this has been an application that a lot of users have been focused on. A lot of people using the ACE2 models have been looking at tropical cyclones and finding quite realistic features in terms of tropical cyclogenesis and things like this. And so this is just showing a map of all the tropical cyclone tracks over the 10-year held out test period. And then finally, we also see that ACE2 responds accurately to the SST variability to El Nino. And so this is showing the surface precipitation response to basically the Niño 3.4 index, so just the regression of the surface precipitation onto that Niño 3.4 index. In the top right, this was kind of the baseline. So this was using our prior model, which was just trained on climatological SSTs. So although in that case we somewhat got the pattern, we did not get the right magnitude of precipitation response. Whereas you can see on the top left, this is the ACE2 model, which has been trained on ERA5, and it does very well in terms of representing the structure and the magnitude of that response compared to ERA5. Now, this was not work that we led, but once we put this model out there, people were using it for a lot of different applications, and so it was interesting to see that this idea of sort of seamless weather to climate prediction actually kind of bore out in this case. And so this was a group from the Met Office that took our ACE2 ERA5 model and applied it for seasonal forecasts. And so they made ensemble forecasts of basically wintertime conditions, so December, January, February average conditions, initialized around November 1st. Now, of course, the ACE2 ERA5 model doesn't predict anything about the ocean. It requires you to sort of provide the ocean condition as a boundary condition. So in their study, they used what they call persisted anomalies. So basically, whatever the anomaly of sea surface temperature and sea ice was on November 1st, they persisted that throughout the winter, which is how actually seasonal predictions used to be made before we had coupled atmosphere-ocean models. And what they found is that although the model wasn't quite as accurate as their state-of-the-art numerical model, it was quite close, which was impressive given that this was not a task that we ever evaluated during the development of this model. And of course, it was much more efficient. So they can potentially use ACE2 ERA5 to boost the size of their ensemble because it's almost free when you compare the cost to their numerical model. Now I want to talk a little bit about downscaling. And so this is our so-called hero ACE model. And so, so far everything I've described is again still emulating either models or reanalysis at that 100-kilometer resolution. But some users, need much more local scale information. For example, reservoir management over regions of topography, amount of precipitation can vary hugely across small distances when we're in mountain ranges, and so having this kind of more local scale information is important for these users. And so we have these simulations, which are kind of remarkable. So this is just showing a snapshot from the X-Shield model, which is a 3-kilometer resolution global model. There's others being developed in Europe as well that can run at similar resolutions. They're incredibly computationally expensive, although now we are able to be able to do these simulations for up to about a decade, 10 years, which provides a pretty incredible training data set for machine learning. So the question is, can we leverage these expensive simulations and use AI to make fast and accurate climate emulators? And so we developed this hero ACE. So hero here means high resolution output. And I'll describe a little bit of our approach of how we tackled emulating this global 3-kilometer simulation. So our training data set, again, we had this 10-year 3-kilometer simulation. We coarsened that basically to 100-kilometer resolution. So we have the same data set, but just sampled down to 100-kilometer resolution. And then we use that to train a version of ACE, or basically our autoregressive global emulator. And so this is trained in the same way as our other models. We did here modify ACE to be stochastic and used a so-called CRPS loss function as a continuous ranked probability score. The important thing here basically is that this helps the model not overly smooth its predictions near the grid scale. And so this makes it more basically amenable to downscaling after the fact, because we have the right amount of power at the small near the grid scales. Now, of course, one question here is we only have 10 years of data from this X-Shield simulation. So typically our ACE models we had trained on at least 50 years of data, and in some cases more like 80 or 100 years. And so can we train an ACE model with only 10 years of data? Our answer is we kind of could, but the errors were quite large in terms of the climate biases. And so we actually took a model that was pre-trained on ERA5, where we had about 80 years of data, and then fine-tuned that on this 10-year global X-Shield simulation, and that improved the skill of the model quite a bit. And then finally, we additionally train, totally independently, we train this regional downscaling model. So it's using the same data set, but this model is now just trained on patches, basically 16-degree by 16-degree patches around the globe, to go from that 100-kilometer resolution back down to the native 3-kilometer resolution. And we do this using a diffusion model similar to the CoreDiff approach from Ardani et al. From NVIDIA. Now, on the other hand, while ACE is predicting a whole slew of different variables at different levels, our downscaling just operates right now just for precipitation, although we'll be adding more outputs to it soon. But we're just basically downscaling the precipitation to this 3-kilometer resolution. So once we have these two models trained, we can now make predictions. And so again, this is kind of a two-step process, although it's much we can do it within the same simulation. And so our inputs again are some atmospheric initial condition, and then our boundary conditions for things like the sea surface temperature. And then we can make an ensemble of simulations. Again, now ACE, this version of ACE is stochastic, so we can make an ensemble of different possible realizations. And so we get this global atmospheric evolution. And then we can apply the downscaling model at any particular region and get the 3-kilometer precipitation, not over the whole globe, because most users don't actually want the precipitation over the whole globe at that resolution. They have some region of interest. And so we just downscale it to that region of interest. And so show a couple kind of results of the quality of this downscaling. So this is just showing on the left a 6-hour forecast initialized from the coarsened X-Shield data, basically for a particular tropical cyclone event or typhoon here. And then you can see the downscaling is really quite remarkable, although we can barely even identify a tropical cyclone in the 100-kilometer resolution. We can reconstruct this And the inputs here are not just the precipitation, but we also use the wind field, which obviously gives a lot of information about the circulation there. And so using that, Hero is able to downscale down to 3-kilometer resolution. And you can compare it to the actual X-shield tropical cyclone on the right here. And not only can we get individual events, we can also get good time mean climatology, which is again another application here. So like the reservoir management topic I mentioned earlier, we care about getting the right climatology of precipitation. So again here, this is showing now 10-year simulation. So on the left is just with the stochastic ACE model, which has been trained on the course index shield data, but is again still just producing that 1 degree data. And so you can see a little bit of amplification over topography, but it's a very kind of coarse-grained view of the Western US. On the right is the actual X-shield model. So this is, again, that global 3-kilometer model. And in the middle is what we get when we apply our Hero downscaling model to the ACE output. So we were able to reproduce all these small-scale influences of topography on precipitation. And generally speaking, most of the biases here are below the noise floor due to the kind of weather variability or internal variability we expect over 10 years, with a possible exception of over the Sierra, which you can see down here, although there's still quite a bit of internal variability there. Okay, now I just want to show a couple other applications here of thinking now about climate change and how we can simulate climate change with these sorts of AI models. So as I mentioned earlier, our approach here has been to emulate numerical model data or output. And so we generated custom outputs from so-called shield model, which is a GFDL atmospheric model. But in order to probe things like the response to carbon dioxide, we coupled it with what's called a slab-ocean model. So this is sort of idealized ocean model, which doesn't have any dynamics, but which can thermodynamically respond to the fluxes of energy at the surface. And so we generate training data with these 3 different values of CO2, kind of present day carbon dioxide, doubling carbon dioxide, quadrupling carbon dioxide, and then train our ACE model with CO2 as an input. And so in terms of getting the time mean climate, we're able to do that very accurately. So here, this is evaluating now on 3 times CO2 value. So this is the value that's inside the range of what we trained on, but is not actually a value of CO2 that the model ever saw during training. So it's basically an interpolation test. And we're able to do very well on that. So this is showing the response basically of the 3x CO2 temperatures minus the 1x CO2 temperatures. And so this is kind of a equilibrium surface air temperature response to tripling of CO2. And we see the expected amplification over land. And in general, the pattern of warming is quite similar to what we have in the reference numerical model. However, if we do another kind of simulation, and again, this is a very sort of classic coupled model into comparison project simulation, which is we abruptly change the CO2 from its present day value to its 4 times value, and then look at the transient response. So not looking at the equilibrium, but just looking at the first 90 days of the response. In that case, the model does very poorly at getting the right timescale of response. So here, what this figure here is showing, in the black lines is again the numerical physics-based model. The dashed one is basically what we expect if you just keep CO2 constant. And then the solid line is what happens when you quadruple CO2. And so you can see that for this is the lowest level air temperature, T7. We have this kind of gradual warming over 9 days of about almost 1 Kelvin. And then in the stratosphere, you have this very abrupt cooling, which we expect is this direct rate of response to CO2 in the stratosphere, while the near surface is kind of mediated by the fact that the ocean has to warm up more slowly because it has this thermal inertia. The blue line is basically our AI model, so it's the one that was shown here, so this ACE2 SOM model. And you can see that it responds very, very quickly. And it turns out it does actually go to the right equilibrium value, but it just goes there far too quickly. So the model has kind of memorized CO2, and it just wants to go immediately to what it saw as the equilibrium value during training for that particular CO2. And so we get this far too rapid response, both in the near surface and in the stratosphere. So that's what we have published. We have been working on improving this, and in particular by adding a more sophisticated training data set that includes some of these kinds of abrupt changes in CO2, and also adds a couple other features like energy conservation, we're able to do very well on this kind of problem. So we can get the right timescales of response, and this is sort of a key, again, as I said, is a very useful test case for climate models to examine different kind of timescales of variability. And then finally, so in that previous case, we were just sort of coupling to this very idealized slab ocean, which is, again, just sort of a thermodynamic ocean. So that was useful for testing some of these ideas like abrupt CO2 changes in an idealized context. But that kind of slab ocean still can't represent a lot of very important variability, like changes in circulation in the ocean or El Niño dynamics, which is a really key part of climate variability. And so for that reason, we worked again with this M² Lines group who had developed this Samudra ocean emulator. So this is a model. It has 19 vertical layers, the same 1 degree resolution, and a 5-day time step. So this has already been trained on ocean-only data. And so we coupled it to ACE by basically having ACE predict the 5-day mean surface fluxes of energy and moisture, and those are provided to the ocean. And the ocean predicts the sea surface temperature, which is provided to ACE, and we have this coupled system that can evolve. We also added a learned interactive sea ice to the Samudra model, and we trained these on, we did train new versions of ACE and Samudra on a pre-industrial CM4 simulation. So we're able to do long simulations. They're stable. They have small climate biases. You can see here, this is the surface temperature bias averaged over the 40-year kind of held out test period. And so we have fairly small temperature biases. And maybe even more interestingly, we are able to actually simulate an emergent ENSO in this coupled system. And so even though, when we're optimizing the models, it's only quite a short window over which we're optimizing these models, we are able to get this slower timescale variability. So you can see Samudra here is in the orange, CM4 is in the black line. And so we are getting these ENSO events where we have perturbations of the Niño 3.4 anomaly, up to plus or minus 1 degree Celsius. However, the magnitude is not quite as strong as what we see in CM4. And in particular, there is still too little power at periods greater than about 4 years. And so the ENSO in Samudra tends to be a little bit too regular at around the 3-year period and doesn't have this longer tail of variability. As I mentioned, we added sea ice to the model. So this is the first emulator that had kind of atmosphere, ocean, and sea ice components in it. So here it was sort of baked into part of the ocean model. And so you can see here, we are able to quite accurately get the seasonal cycle of sea ice extent shown in the left figures, and also the time mean patterns of sea ice, both in the northern hemisphere and in the southern hemisphere. Now, again, why are we building these models? We already have all these great numerical physics-based climate models. So why are we building a whole new set? I think the clearest selling point here is the efficiency of these models. And so here, this table is showing basically both the inference throughput. So basically how many simulated years can I do in 1 day of wall clock, real time, and also the energy cost. So of course, we're running these different simulations on different hardware. So just comparing the throughput is a little bit tricky, but we can compare the energy cost in more of an apples to apples way. And so these left two columns are showing the numbers for these two numerical models that we are emulating. So the left is the C96 shields is 1 degree resolution. So this is kind of comparable to what we expect for most, coarse resolution atmospheric models. So running on about 1,000 CPU cores, we can do about 10 simulated years per day, and energy cost about 8 kilowatt hours per simulated year. The axial model, again, this is a global storm resolving model. These are incredibly computationally expensive. So we have to run it on almost 30,000 CPU cores. We only get about 0.1 simulated years per wall clock day. So for example, the 10-year simulation that we trained on took about 3 months of time to actually complete, using a significant fraction of a large supercomputer, and has this relatively large energy cost. Now, the AI emulators that I discussed are shown here now on the right. So these are all running on a single GPU, it's a high-end GPU, an H100, although they can actually run on simpler GPUs and even run on your laptop as well. The simulated years per day for the global ACE model is about 1,500 years. So this is over 100 times faster than the coarse resolution model. And in terms of energy costs, is almost 3 orders of magnitude less. For the downscaling, here I'm comparing downscaling just a single 16 degree by 16 degree patch. So, we're not getting as much output as what we would get from the X-Shield model, which gets you 3-kilometer data across the whole planet. But, I actually would argue that this is not necessarily a bad thing. We're still simulating at the coarse resolution the model with the same accuracy as X-Shield. And most users really just want that fine scale information in certain regions. And so the flexibility of AI is that we can just get the outputs that we want and that we actually need at those resolutions and simulate everything else at that coarser resolution while still being much more accurate than we would get with a numerical model running at that coarse resolution. So in terms of the simulated years per day, the downscaling is actually relatively expensive compared to the ACE model because we're using diffusion, so it takes quite a few steps and predictions to get the final high-res image. We're still able to simulate about 30 years per day for that single patch. In terms of energy cost, this is a huge reduction over what we get for X-Shield. Again, X-Shield here would be representing the whole globe. Here we're just doing a region, but I think in some ways this is actually a feature of our approach. Okay, this is kind of the last result I want to share, and I'm happy to take some questions. So I just wanted to advertise that our group has been leading in collaboration with Nikolai Koldanov and Christian Lessig, this AIMIP, so AI Model Intercomparison Project. And so here the goal is to do an intercomparison of different AI emulators that have all been trained on ERA5 and evaluate them in a consistent way and also collect the outputs of these models in a format that is the same as the existing CMIP6 and CMIP7 archives and distribute this so that users can more easily analyze the outputs of these models and compare them to existing numerical simulations. So we already have 6 models that have submitted simulations for this. We're doing the initial analyses and we'll have a preprint and be releasing this data set soon. So keep an eye out for that. But I think there'll be a lot of interesting results and things to learn there. And then the last thing I want to say is, our ACE models are all openly available with Apache 2.0 license. So the links here are both to the Hugging Face repository, that's the QR code. And so that's where you can find all these different models that talks about, which are available. I would say they're quite easy to use, especially compared to any kind of numerical climate model. And so you can download the checkpoints. The code to run these models is just a single Python package that's very easy to install. You can run it on CPU. It'll be a bit slow, but it does work. Or of course, an NVIDIA GPU is fast, or even on Apple Silicon, they run quite quickly too. So we have these model checkpoints. There's a code base you can see and documentation as well there. So please check that out. And yeah, just finally to kind of summarize, I think AI models provide a fast and flexible approach to climate modeling and to climate model emulation. Our ACE model is an efficient and seamless emulator of existing atmospheric models, which can be used for long-term simulations of a broad range of climates. We've done this in different climates, as I say. We've done this in coupled atmosphere-ocean contexts, and we're now developing downscaling models to get the outputs at that 3-kilometer resolution. And of course, one of the big advantages here is that these models are easier and much faster, orders of magnitude faster to run than the reference models. In terms of next steps, we want to enable this downscaling and coupled modeling in a wider range of climate scenarios. But there's still kind of like a big question here is, how well can these models generalize usefully well outside the range of our training data? And so, our approach here has been to train on climate model output, which is great. But of course, training on ERA5 is very appealing too, because there is a lot of variability and a lot of phenomenon that are much better captured in reanalysis than in any current existing coarse resolution climate model. So, I think a big question is, can we train on ERA5 and somehow use those learnings into the future as well? And that's still a big open question. So yeah, with that, I'll take any questions. Thank you.
Okay, Thanks very much for the nice talk and sharing the very comprehensive and very nice work. And there is some questions from our audience, and it is possible to use the model to calculate the wave height forecast.
Yeah, we haven't directly predicted wave height, but I think this would certainly be something that would. I mean, we do predict the near surface winds, like the 10-meter winds, which I think would tell you a lot about the wave height. So I think this could be. Yeah, I mean, these models, it's possible to basically do some fine tuning and add new variables to them. And so, for example, for the AI MIP, for this case, we actually took an existing model and just fine tuned it to add new pressure level outputs. So potentially something you could also do for the wave heights as well. But we have not actually done that ourselves.
Okay. Nice. And there is also some questions about the historic data. And then there is a questions comparing on historical data. There are areas where neural networks significantly over or underperform numerical simulation.
Um, so the question is there areas where the neural network underperforms? Is that what the question was?
Yeah, overall
Yeah,
underperformer.
yeah. I mean, I think people are still working on like getting good stratospheric variability. So it's something that I didn't show in this talk. So our model that is trained on ERA5, it does get plausible stratospheric variability in terms of things like sudden stratospheric warmings, but whether those are properly connected to like tropospheric conditions, I think is an open question. I know in the kind of weather forecast settings, it seems like these models are not very good at predicting those sudden stratospheric warmings. And then also like our model, even though it's trained on Area 5, which does represent the quasi-biennial oscillation, our model does not properly simulate that. It just kind of goes back and forth between the eastward and westward phase, but not with the correct periods. That'd be one situation where some numerical models do better, although that is also a challenging thing for numerical models too.
Yeah, and yeah, and there is also a questions from our audience, and they are wondering your opinion on the current performance of AI weather emulator and forecasting models on extremes, like some heavy precipitation, heat wave, or so on. And then can you see they are very useful for generating and anticipating record breaking or record shattering extreme event at current stage. I think this kind of common issue for the all AI related work because this data is out of distribution of the training data and it's not. So do you have some opinion on that?
Yeah, I mean, I think there's definitely some literature showing that these models can learn something from one region of the planet and sort of I would say sort of apply it elsewhere in some sense. And so I think the question, part of the question is this record breaking in sort of a global sense, or is it record breaking for that region? I think for the latter case, actually, these models probably would be able to do pretty well, and that's what we've seen. But if it's sort of an absolutely unprecedented data set anywhere on the planet, it's never been seen in any way by the training data, then yeah, I think we have seen that, for example, models that are trained on an artificial data set that has kind of none of like the most extreme tropical cyclone events also struggles to predict those strongest tropical cyclone events. So yeah, I think that can be a challenge, but I think again, the way you formulate the training can make a difference here, and potentially some of these sort of more hybrid approaches or more local AI prediction approaches can help with that.
And I also have a following up question in terms of that, because we make a lot of effort to downscaling the data, and maybe I'm not sure if we can get more extreme event after we get the high resolution data, or compare with the coarse data. Maybe it's kind of a possible option to improve this in terms of forecasting or predicting the extreme event in the future.
Yeah, I mean, certainly, I mean, like you can see in this example here, when we do the downscaling, the maximum values, the precipitation rate, and then the downscale output are much higher than any of the values in the 100 kilometer. So yeah, we have looked, this is a preprint you can find in archive. We have looked more quantitatively at like the PDFs of the precipitation, and certainly the downscaling does introduce values which are higher than anything we've seen in the course model. But there still is sort of like a tail of the very most extreme events in this extra simulation, which our model doesn't necessarily represent. Although I think there's some question whether these are actually realistic events in the numerical model itself or some sort of quirk of the numerics.
Yeah, and I also following up questions because you have mentioned in the slide presentation that 4 times carbon dioxide scenario is not so good. And then is there any possible is called a reason because of this extreme event because the very high carbon dioxide maybe cause more data shift, data distribution
Well,
shift or something like that? Mhm.
I think in this case, we were trained like so for these for this paper here, we were training on the 4 times CO2 simulation, so that was part of the training data. So I don't think that was necessarily the issue. I mean, the problem here was that basically the model, and we also see this in the context of like 20th century warming, where we have the sort of monotonic increase in CO2, the model often will use CO2 as sort of a clock variable. It kind of basically there's a one-to-one relationship between CO2 and like what year it is in the historical record. And so basically we do see sometimes these overfitting issues where the model will use that and be overly indexed on the CO2, even though it's not really what was driving some kind of variability. And so in this particular case, you see it in terms of it immediately going to that equilibrium state, even though in reality there should be some thermal inertia in the ocean that slows down these responses.
Yeah, and also there is also a following up question in terms of this extreme, event, and they want to ask, do you think there are any that there are steps that are still missing for AI application to extremes, or are there fundamental limitations for the use of AI in this setting?
I mean, I think there's still progress happening. I mean, I do think that we've already seen that the things like the loss function used have a big impact on this. So the first generation of weather models were all using some kind of mean squared error type loss, and this did cause issues for extremes. And more recent models, which are using some kind of stochastic loss function, which encourages the model to have the appropriate spread in its predictions, then we see that helps with the extremes. And then also these kind of more recent generative models, based on diffusion or other approaches, again, are also quite good at capturing the distribution. So I still think that there's hope that we can, improve the current fallbacks in terms of precipitation, in terms of prediction of extremes.
Mhm. Nice. Okay, so the next questions, so under rapidly changing conditions, such as Antarctic, and where the katabatic winds frequent occurred, and the weather is highly variable, how does the model perform? I mean, in terms of the region, very complicated, with complicated situation, very high fluctuation. Yeah.
Yeah, I mean, I don't think we've focused too much on analyzing some of like those details in the Antarctic. We certainly in past work and kind of our work doing these sort of hybrid simulations, Antarctica is certainly a challenging area because its dynamics are so different than the rest of the planet, and it also represents such a relatively small fraction of the area of the Earth that it often was challenging for the machine learning to sort of properly simulate Antarctica and the rest of the planet well at the same time. That was kind of in our prior work, and we haven't seen any particular issues in these kind of global emulators with Antarctica. So here again, this is just showing the sea ice, but this is also kind of related to the biases and surface air temperature. Here, this is showing just the actual surface temperature itself. So it does not seem like Antarctica was sort of popping up as a particularly problematic area, at least in terms of sort of climatology. But yeah, we haven't looked at some of that variability as much.
Mm-hmm. So, mm-hmm. So currently it's not very big issue, right? In terms
Yeah,
of
we haven't noticed any particular issues there.
yeah, okay. It's very nice because I noticed there is also very nice in terms of the achieve the mice or energy conservation law because you show that because yeah, a lot of AI driven method and yeah, we need to respect the fundamental physical conservation law, right? And so. Especially during when we simulate the very long term and simulations, and how does your team act for these models to balance the flexibility and the speed of the deep learning with the strict physical constraint required for the accurate atmospheric modeling? Because I noticed there is a very good performance in AI2. Yeah.
Yeah, I mean, so our approach has been to be fairly, you know, we're fairly restricted in terms of like exactly which physical, laws we're trying to impose. So we're not. I think there is some risk of being like too heavy-handed with this, but basically we, in our most recent models are basically, requiring that, fluxes which should be positive are positive. So things like precipitation. I mean, this is a fairly straightforward thing to do. There's kind of no reason not to do it. And then we basically impose just global conservation of basically the dry air mass, and that actually did help our simulations quite a bit. We often previously had unrealistic drifts in the global mean surface pressure, and imposing that you basically have constant dry air mass, remove that. So basically just whatever it is in the initial value, it has to maintain that. And the way we do these corrections, we basically it's just a layer in the network, at the end of the network where we will modify a certain variable such that our balance holds. So for the dry air mass, for example, we would modify the surface pressure such that there's no change in the dry air mass. And then we do a similar thing for the global moisture. So basically that evaporation minus precipitation equals the change in global atmospheric moisture. And then for the energy conservation as well, that the balance of fluxes at the top of atmosphere and the surface are equal to the change in the moist static energy of the atmosphere. And so yeah, those things are useful for interpretability. I would say we haven't found as much evidence actually that the energy and moisture conservation make like a really clear difference in the simulation, but they're useful for interpretability. And then finally, in the ocean, we haven't published any work here, but we are also exploring some of these kind of correction strategies in the ocean where we do find they're quite useful for getting sort of appropriate long-term trends in ocean heat content uptake as CO2 increases.
Mm-hmm.
But yeah, we're just kind of imposing these global constraints, so they are still fairly minimal constraints. Yeah.
Okay, nice. Okay, also more questions from our participant. Okay, so are there ways to pose soft bells to encourage the model towards the desired physical balance? For example, penalty term for an off balance where there shouldn't be one.
Yeah. So I mean, our strategy is just these kind of loss function modifications. It can be a lot of like hyperparameter tuning required of like balancing the different terms from the loss function. So for our constraints that we're imposing, which are things like the energy conservation and moisture conservation, I mean, these are exact. We expect these to be hold exactly. And so again, as I said, it's basically a hard constraint that we build into the network where we modify one term. But we do this during the learning, so it's accounted for in the loss function. It's not just like a post hoc thing we do at inference time. It's during the training these things are turned on. So that's been our strategy. I know I know some other groups have explored like trying to impose something like hydrostatic balance or things like this through loss function penalties, but it's not something that we have tried.
Okay, very nice. Okay, so we are nearing the end of our time, and thank you very much, Oliver, and for the very excellent presentation and very insightful discussion, and also thank you to the audience from your engagement. And okay, so if there are no more questions, then we can conclude our session, and we will play the closing video later, and then have a good
Thank you
day.
very much, Lou. Thank you, everyone.
Yeah, thank you very much, Oliver. Yeah.
Thank you for participating in today's AI for Good session. We hope you've learnt something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for good.